Good evening everyone, I'm a presenter Jae-sung Choi. Let me start my presentation about volumetric propagation network, stereo LiDAR fusion for long-range depth estimation. The paper ID is 3543. Stereo LiDAR fusion is one of the promising modalities in that it can utilize multiple sensory data such as two RGB images from stereo cameras and point clouds from a LiDAR sensor. Compared to existing methods such as stereo matching and depth completion, stereo LiDAR fusion can be viewed as a combination of stereo matching setup and depth completion setup. While deep learning based stereo matching and depth completion largely improves the quality of depth, we present a new possibility of stereo LiDAR fusion that can further improve the quality of depth and lessens the dependency on a LiDAR, which can be helpful for safety driving in autonomous environment. Let us compare the quality of the estimated depth from stereo matching, depth completion, and stereo LiDAR fusion. The chart is about depth performance in KT depth completion benchmark using validation set. According to this chart, LiDAR is a dominant sensor in that it can be helpful for estimation of high quality depth, and stereo LiDAR fusion can be further increase the quality of the depth by using the additional image information and compared to the recent depth completion methods. This is the one reason that can demonstrate the why stereo LiDAR fusion is a promising modality for high quality depth estimation. Then the following question is how we can design stereo LiDAR fusion, or what is the issue in stereo LiDAR fusion? Throughout this paper, we address the way of the fusion of stereo image and point cloud is a fundamental problem in this task. Recent deep learning based stereo LiDAR fusion networks propose their own fusion scheme. One of their common strategies is about the 2D image domain fusion, which needs to project 3D point clouds into image domain in a pre-processing stage. In brief, 2D fusion is designed to fuse RGB image as well as sparse depth maps in a pixel-wise manner. However, neighboring pixels in a 2D image domain are not necessarily adjacent in a 3D space. 2D fusion can lose depth-wise spatial connectivities, which cannot be an appropriate fusion scheme. To overcome this issue, in this paper we propose a geometry-aware stereo LiDAR fusion network for long-range depth estimation called volumetric propagation network. The key idea of our fusion is related to the fusion volume that can align stereo images and point cloud directly in 3D space. For easy understanding, we include simple visualization of 2D fusion and our 3D fusion. Since our 3D fusion maintains the 3D geometric relation between stereo images and point clouds, we can simultaneously compute matching cost between stereo images and point clouds. However, for 2D fusion, it can lose depth-wise spatial connectivity between sensory data since they fuse in a 2D pixel level. Typically, in our 3D fusion, we directly embed point clouds into 3D fusion volume to maintain metric accuracy of point clouds. To do so, we formulate stereo LiDAR fusion as a volumetric propagation, and we can compute matching cost between stereo images and point clouds simultaneously. Thanks to our fusion volume, we can improve the quality of long-range depth from our volumetric propagation network. To further accelerate our 3D volumetric fusion, we introduce a new convolution kernel for low-level fusion called FusionConv. The key idea of our FusionConv is to aggregate colorized point features in consideration of their 3D local responses between neighbor point clouds as well as neighbor pixels. Since our fusion volume contains each input feature along the channel axis, low-level fusion through our fusion conv acts as initial alignment of local responses in features. This is the result of our depth estimation in KITT completion validation benchmark. It shows that our method outperformed recent stereo LiDAR fusion method as well as existing depth estimation methods such as depth completion and stereo matching. This is a qualitative result on KITT dataset. We typically compare ours and recent stereo LiDAR fusion method called CCBM. This is another qualitative result on the virtual KITT dataset. It demonstrates that our method largely outperforms the recent stereo LiDAR fusion methods, and we can estimate more accurate depth measurements in distant region. We conduct an ablation study about type of volume by comparing coarse volume, depth volume, and fusion volume. Different from depth volume, our fusion volume directly builds metric unit volume without intermediate transformation. Such direct construction is to minimize the loss of metric accuracy from point clouds after embedding. Finally, our ablation study supports the necessity of our fusion volume and demonstrates higher accuracy than others. The next ablation study is about fusion conv. As far as our understanding, this is the first convolution kernel for low-level fusion of heterogeneous sensor data. So we compare our fusion conv with simple MLP-based network and naive point clouds without fusion. The table above shows that our fusion conv effectively increased the performance of the estimated depth. Such results imply that low-level fusion to align local responses of each sensor data is also important issues for stereo LiDAR fusion. This is an ablation study about our 3D fusion. It shows that our 3D fusion is particularly helpful for the depth improvement compared to the 2D fusion. This is the last ablation study about dependency on input point clouds. We provide 4 different depth maps that take 15,000, 5,000, 1,000, and 10 points as an input of our network as well as stereo images. It demonstrates that our network robustly infers depth maps based on given stereo images without changing any hyperparameters or fine-tunings. Conclusion: we propose volumetric propagation network for long-range depth estimation by stereo LiDAR fusion. We introduced fusion volume that simultaneously computes matching cost between stereo images as well as point clouds while maintaining their 3D geometric relation. We designed fusion conv that performs low-level fusion of input sensory data to further facilitate the fusion at our fusion volume. Thank you for your listening.